A man is running around a circular track that is 200 meters in circumference. An observer uses a stopwatch to record the runner's time at the end of each lap, obtaining the data in the following table. A. What is the man's average speed or rate between 68 seconds and 152 seconds? So let's just imagine that here is our circular track and here is our man. And he starts running around the track. And when he gets back to the beginning, they're telling us that that's 200 meters. But then he keeps going around. And the second time he goes around, it's 400 meters. So, and then he goes around again and again and again. Every time he goes around the track, it's an additional 200 meters. So we'll just make a column for our meters. And in this column, what they're telling us is when he goes around, somebody is standing there and looking at their stopwatch. So the first time he goes around, the time shows that it took him 32 seconds to get around that first time. And then he ran around again, and that meant that he went 400 meters, and the time that has lapsed so far is 68 seconds. So these are like the totals. You know, this is a cumulative number, 68 and 400. So, and this went on and on and on until he went around several times. So the third time he went around, that would have meant he went 600 meters, 108 seconds, and then on his next lap around, that would mean he traveled 800 meters total, and that read on the stopwatch 152 seconds. Next lap meant he went 1,000 meters. Stopwatch read 203 seconds. Next lap meant he went 1,200 meters. That read 263. Next lap meant he went 1,400 meters. Stopwatch read 363. And his last lap meant that he went 1,600 meters. And that read 412 seconds on the stopwatch. So the question is, what was this man's average speed between 68 seconds and 152 seconds? So they're asking for this interval between 68 seconds and 152 seconds. So they're asking for this span. They're not asking for just his speed at 68 seconds. They're asking for an interval. Well, speed as we know it, we generally think of speed as miles per hour, like in a car. So speed is really just distance over time. So we can write that speed equals distance over time. In our case, the distance is measured in meters and the time is measured in seconds. So ours is going to look like this. S equals meters over seconds. Now, since they're looking for an interval for the speed, it's really called the average speed. So with the average speed, how would I get the meters? How would I get the seconds if I'm given all these numbers? Well, this interval here is from 400 meters to 800 meters. So we can just tell by looking at it that that's a span of 400 to 800. Well, that's a span of 400 meters. Well, how would we show that mathematically in this formula? Well, we could just say the average speed, because it's an interval, so I'm using the word average, is 800 minus 400. That's the interval that we are referring to, meters. And at the same token, what are the seconds that we are referring to? Well, we're not referring to the 32, we're just referring to this interval. So that's the interval between 68 seconds and 152 seconds. So that's the same idea as the numerator. We just subtract the two numbers to get the difference between these two so we can get the interval. 152 minus 68 seconds. So then we'll just simplify. We get 400 meters on top, and 152 minus 68 is 84 seconds. Now, if we want that to look like an average speed, we usually have a 1 in the denominator. Just like in a car, we usually say, okay, I'm driving 30 miles per hour per 1 hour. So to do that, we just divide both numerator and denominator by 84, because that'll give us a 1 here, and then our 400 will be also divided by 84. I'll just do it again down here. 400 divided by 84, and 84 divided by 84. It's as if we're dividing by 1. So we end up with 1 second, which of course I don't have to write the number 1, but that's okay. And then 400 divided by 84 is about 4.76 meters per second. So it's about that. I rounded. So that is our speed, our average speed. I'll just rewrite it again here. From 68 seconds to 152 seconds. So to see that interval on our diagram, let's go ahead and get a better circle. And we'll just get rid of this one. So then this represents the track, and the first time he goes around, let's just say he starts right here, and he goes around, and there's a person standing here with a stopwatch, and that distance he traveled was 200 meters, and at that point the stopwatch showed 32 seconds. So that just brought us to the end of this first lap here. So now we're going from the first lap and starting our second lap. So we were at 32 seconds here, and then as we travel some more, it'll be 33 seconds, 34, 35, and so on as we travel around to get to the end of our second lap. And at the end of that second lap is when the stopwatch shows 68 seconds at the end. So now we've traveled 400 meters, and the stopwatch shows 68 seconds. This is the point here where they want us to start finding the average speed of the runner, because they said they wanted it from 68 seconds, which is right here at 400, from 68 seconds to 152 seconds. So at this point is when I should change my color to red, because that's what this interval represents, or vice versa. That's what this diagram represents, that interval. So I'm going around 68, maybe I'm at 80 seconds, 90, 95, 100, 108 seconds. So this is at the 600 meters, and the stopwatch reads 108 seconds. And then he keeps running, 108, 120, 130, 140, 150, 152 seconds at 800 meters. So if you look at it that way, which is the correct way, you can see that this interval that they're asking us to find the average speed really only covers 400 meters. Even though it looks like it's 3 laps, we don't start counting until after the second lap. This 68 seconds is not until right here. And you can see there's only 2 laps there in red and 2 laps here in red. So this outer green rotation represents him traveling at the end of his first lap and coming all the way around and completing this second lap. So if you want to think of it in this manner, from 0 up here to this first lap, that's really this notation or symbol really symbolizes lap 1. And then at the end of lap 1, he had 32 seconds. And then this one really symbolizes lap 2. This is lap 2 coming around. And at the end of lap 2, the watch shows 68 seconds. And the question wants us to take the interval between the 68 seconds, meaning the end of lap 2, to 152 seconds, which would represent the end of this lap, which is, if I keep doing this, from 68 to 108 is lap 3. From 108 to 152 is lap 4. And so these, even though these aren't circles, these little pathways symbolize the lap, symbolize him traveling in the circle. So once you have that in your head, when you look at these type of problems, you won't get confused when you have to go over and do your subtraction for your change in position or change in seconds. Now the word change that I just used should be a tip-off for you. Let's go to the next question and see if you know what I mean by tip-off and change. So the next question asks, what is his average speed between 263 seconds and 412 seconds? Well, do this in blue. That's this interval here, 263 to 412. So again, this was lap 4. If I drew another symbol, this would be lap 5. This would be lap 6. This would be lap 7. and this would be lap 8. And I should be saying the end of lap 8, because then he's finished. End of lap 7, end of lap 6. So to find the average speed for this interval, it's the same idea. So our average speed, and I'll just call this sub 2, speed average speed A sub 2 equals, well, what is our interval here? What is our change from 1200 to 1600? Well, we know it's 400. We could just do that in our head. So let's write it out mathematically like we did up here. So to find the change then between 1200 and 1600, we'll just write 1600 minus 1200. Meters. And then it's the same concept. What is our change in seconds so that we could get just this interval? Well, our change in seconds would be 412 minus 263 seconds. And if we reduce that, I'm going to run out of room. If we reduce that, we have 400 meters per 149 seconds, which further reduces then 400 divided by 149 equals 2.68 meters per second. So that's our speed in this interval, our average speed in this interval. So the question is, did this runner slow down or speed up towards the end? Well, up here in this interval, he was running at 4.76 meters per second. So he was covering a lot of ground for each second. But towards the end, he got tired and he was only traveling 2.68 meters per second. So that's quite a decrease. So he slowed down. So if you think about it, this process that we went through of finding the average speed, we did it by taking an interval and finding just the span for that interval. And we found that span by taking the change in the span. So if we think about what we've learned so far, what other concept takes the change of one variable and puts it in the numerator, and then puts the change of the other variable in the denominator. Change in one variable over the change in another variable. Well, we remember that to be slope, and slope is generally written as m, but since we're already using m in this equation, I didn't want to confuse you, so I wrote it out. But the slope is usually the change in the y coordinate over the change in the x coordinate. That's what slope is. You're probably used to seeing it as y2 minus y1, that's your change, over x2 minus x1, change in your x's. And we can go ahead and graph these points just the same, as we would any other algebraic problem. So let's go ahead and do that. I set up a graph, and you might wonder, well, how did I know to put the seconds on the x-axis? Well, the reason I knew to do that was because since our slope is the change in y over the change in x, distance over time is speed, and average speed is the change in distance over the change in time. Since time is in the denominator for speed, and speed and slope are basically the same thing, then since slope has x in the denominator, then I should make the x-axis my time, just like the slope. So let's go ahead and try and plot these points real quick. So at 200 meters, the stopwatch showed 32 seconds. So at 200 meters, this is my y, 32. So 32 seconds is about right there. 400 meters, 68 seconds. 400, put that there. 600, 100. 600 meters, 108 seconds. 800, 152. 1,000, 203. 1,200, 263. 1,400, 363. got a little big. And 1600, 412 seconds. Okay, so if we went ahead and connected all of these points, we would kind of see that it doesn't seem like it's making a straight line. And it actually seems like after 1200, or this interval here, here's the 1200 and the 263 seconds. After that, it really starts to, it doesn't look like it's going to be a straight line. And it's not. And that's because he was running and his speed is inconsistent. And if he ran the same speed the entire time, then yes, we would have a straight line with only one slope. But he didn't do that. He ran fast at the beginning and he ran slower towards the end. So how do I know that? Well, if I look at the computation that I did here, I took an interval in red between 400 and 800 meters. So that would be from 400 here to my 800 mark there. I connect those points, and lo and behold, I get something that looks like a line, and I can see it's sloped in a certain way. Well, what is that slope? Well, that slope is the slope that I computed up here, where I did take the change in y's, which is this 800 minus 400 over the change in the x's, which is the 152 minus the 68. And that gave me the slope of the line between the first point of that interval, 68, 400, and the last point of that interval. So this slope came out to be approximately 4.76 meters per second. So instead of writing slope, I'm just going to write the average speed, because that's what the problem was about, and we know that average speed and slope are the same thing. So my average speed was, or is, 4.76 meters per second. That was for that interval. And the other interval are these points up here. Actually, these last 3 points. But I only measured the slope on the first and the last point when I did this computation here. So if I want to see the slope just for this interval in this computation that I did, I'll just draw a line connecting the first and the last point, to emulate what I did with my computation. So those 2 points would be 1200 on the y and 263 on the x. So 1200 and 263, it's right here. Actually, let me grab the blue. So from there to my last point up here, it's 1600. So there's my line. It's more like a line segment connecting the first and last data points of this interval. And that should represent my slope between these 2 points, which should be the 2.68 meters per second, which is also my speed. So this line then would be speed, the average speed sub 2 should be 2.68 meters per second. And just to emulate what I did down here, I can show it up here as well. My change in my y was 1600 minus 1200, so 1600 minus 1200 represents this, and this length is 400. And just like what we got here, and then my change in y's are the 412 minus the 263. And this is 149. So I can write those in. This was 400. This was 149. This one was also 400, but, whoops. But the difference in the x's was 84 up here, 84. So you can see on this one, yeah, 84 is a smaller number, but guess what? That just meant that he was running faster because he took less time to cover the same 400 meters. Here it took him 149 seconds to cover that 400 meters. And you can see how the slope is, they're both increasing, but this slope is increasing at a slower rate. Hence, he was running slower. And this slope was increasing quicker. And just so you know, if I had a good enough pen for this program, if I were to connect all the dots and not just with straight lines, because of course, you know, look at this dot, it's not even connected. Well, that's because we didn't count it when we were doing our slope computation. We just kind of ignored it and just took the distance between these two. But if we figured out what the equation was for this curve, because it will be a curve, it's not a straight line, it's got inconsistent slopes. If we did figure out the equation for it, it would be curvy. And I could probably kind of show that maybe in yellow. If I can try and connect them. So let's see if I can do it. And now here I kind of curve down and then back up again. So if I were to take the average speed between, say, this point and this point here, I would get a totally different slope than the one I got between this point and this point. So between these two, if I mark it, I only have 4 colors, so I'll have to use red again. So you can see that slope is different. And this slope here then, between these 2 points, it's a less steep, it's a shallower slope than the blue one. So if the red is shallower, does that mean that he ran slower here or faster than the blue? Slower, yes. And we could see that if we went ahead and did our average speed for just these 2 points between 1200 and 1400 meters. So this would be like the third average speed. So I'll go in red since I did make that red. So this will be a sub 3 speed, and we're going between these two. So the difference in the y's would be 1400 minus 1200. That's meters. And the difference in the x's would be 363 minus 263 seconds. And that would be 200 meters per 100 seconds, which equals 2 over 1, so that's 2 meters per second. So that's what this slope would be then. So this slope, a sub 3, is 2 meters per second. And it is slightly slower than the blue. Not by much, but it is a little bit. So you may be wondering, why are we finding the speed in this manner? You know, doing the subtraction, doing it using change in y over change in x. Why don't we just take our meters per second right from our chart, and we have all the numbers there? Why don't we just find our speed that way? We have a formula for speed, meters over seconds. Well, the reason we don't do it that way is because, first of all, if we were to take, say, just say we took lap number 6 here and said, okay, well, I'm just going to use the 1200 and the 263 and find my speed that way. S equals 1200 meters divided by 263 seconds. And so 1200 divided by 263 is 4.56 meters per second. And you may think, well, that's okay. I can live with that number. That sounds reasonable. Maybe not for this slope here between this point, the 1200, and the 1400, but if we were to pick a point, say here, to the 1200, this slope really didn't change that much from here to there, so why can't I just use that? Well, for one thing, we may not always be this lucky. We may have a graph that's very wildly changing speed, and so it's just going to be, like all over the place. And many times we don't have the luxury of seeing the graph and we don't know. That's one reason. The other reason is when you just take the one data point, say this one, we'll just keep concentrating on the one we just did. You're taking the 1200 divided by the 263, you're taking it as an average of everything from the beginning. In other words, what you're subtracting here is 1200 minus 0, 263 minus 0. So it's a pretty big, it's a pretty big span that you're taking. So what's better is to rely on the average speed and just make your intervals smaller and smaller and smaller. And that's what calculus is. And that's actually how a police officer figures out what your speed is. He takes a laser gun and he shoots it at your car as your car is going along. Just say this is your car here. And then it's in that position. And then a split second later, he takes another picture of your car and he's got a little grid. He doesn't know calculus. It's all done behind the scenes, of course. And that computer of his will then connect the 2 points, make a line, take the slope of that line just like we've been doing, and that slope is his speed. And he's pretty confident that he clocked you at the correct speed because his points were so close together. And that's the beauty of taking the change in y over the change in x, or the average speed over a shorter distance. So there's just so many applications to calculus once you know, stick with it and keep learning more. And it can really be a lot of fun, especially if you can think of interesting real world examples. All right. Well, I hope I've helped you. I hope you've enjoyed this tutorial. I certainly enjoyed making it. And I'll see you later.